Hello, I'm Tsumugi Ida from Keio University, Japan. In this presentation, I would like to introduce a paper titled Visual Explanation Generation based on Lambda Attention Branch Networks. First, I'd like to introduce the background of this study. Visual explanations for deep neural networks are important in terms of enhancing accountability and providing scientific insight to experts. For example, this figure shows a magnetogram, which is a solar image concerning a phenomena called the solar flare, whose theoretical background remains unclear. The region circled in red, where the model has focused its attention, may be the key to understanding the solar flare. Next, this slide introduces the problem statement. In this paper, we focus on the task of generating visual explanation for classification problems. The input is an image, and the output are predictive class and visual explanation. Attention map is used as a visual explanation, and the pixels of high importance are visualized in red, and those of low importance in blue, as shown on the right. Next, this slide introduces related research concerning explanation generation. While explanation generation for CNNs has been widely studied, explanation generation method for transformers has not been fully established. Attention rollout is the explanation generation method for transformers. Also, RISE is a generic method for explanation generation. In this paper, insertion deletion score, which is a standard variation metric of visual explanation, was also proposed. However, the problem with the existing method is that visual explanations of lambda-based transformers focus on generic images. As will be discussed later in the presentation, the insertion deletion score is inappropriate for images with sparse important regions. Next, I will explain the Lambda networks. Lambda networks is an image-specific transformer proposed by Bell et al. It can capture a wide range of relationships with less computation than VIT. In the proposed method, we generate explanations for Lambda networks. Next, this slide shows the computing process of the Lambda layer. First, input of the Lambda layer is denoted as H. H is transformed by convolution to generate query, key, and value. Softmax is also applied for the key. Next, Lambda P is obtained by applying convolution to value, and Lambda C is calculated as a product of key and value. Finally, the output of the Lambda layer is computed by this equation. From these computational processes, Lambda C can be considered as a compression of Q. From this structure, there are mainly two strategies to calculate attention. One is to simply visualize Lambda C as in attention rollout. However, this approach was not able to produce clear explanations. Another strategy is to use a module dedicated to explanation generation. We choose the latter for the proposed method. Next, I will introduce the novelty of this paper. In this paper, we propose the Lambda Attention Branch Networks, LABN, which generates visual explanations for lambda-based transformers. LABN generates clear explanations by introducing the Lambda Attention Branch, a branch structure dedicated to explanation generation. From here, I will explain each of the modules. The first module is Lambda feature extractor LFE. LFE extracts feature H from an image. The Lambda layer is part of the bottleneck layer as shown in this figure. Next is the Lambda attention branch, LAB. LAB generates an attention map of size 1 times H times W. The attention map generated by the LAB is used as a visual explanation. Finally, in this slide, the Lambda perception branch is shown. The LPB performs classification. The input of LPB is the adder product of the image feature H and the attention map alpha. LABN can use the attention map not only as an explanation, but also for highlighting important areas for classification to improve accuracy. We introduced saliency guided training, which has been successfully applied to gradient methods to reduce noise in the attention map. This slide shows an overview of saliency guided training. First, based on the attention map, a mask image X field is generated by removing unimportant regions. Then, a loss to minimize the KL divergence between Fx and Fx field is introduced. Next, I will introduce background for the proposed metric. The deletion score, what is a standard metric, measures the change in the probability of a predicted class when pixels are deleted, according to the importance given by an attention map. The main problem with the deletion score is that it is inappropriate for images with sparse important areas and uses out-of-distribution images. For images with sparse important regions, a coarse explanation may result in a higher deletion score than a detailed explanation. For example, in a solar flare image, the percentage of sunspots that are considered important regions is very small and sparse. The deletion input for the coarse and fine-grained explanation is shown in the image. Deletion input for the coarse explanation appears to be more largely deleted than the fine-grained one. Given this background, we propose a patch insertion deletion score, PID for short, as a new evaluation metric for explanation. The PID score is a patch-based insertion deletion method. This video shows the insertion deletion process of the PID score. The PID score is calculated by following process. First, we divide image X into patches and insert delete patches based on the importance score. Let's call this Pij. Then, we plot N with the predicted probability, and PID score is computed as the AUC of this plot. This is the experimental settings. We conducted experiments on two public datasets, IDRID and different magnetographs. IDRID is dataset for detecting diabetic retinopathy from retinal fundus images and its binary classification task. Different magnetographs is a dataset for solar flare prediction. The dataset also focus on binary classification task. The breakdown of the divided sets are shown in the table. Next shown is a quantitative result. We evaluated the models by the ID and PID scores. This table shows the results for IDRID. The LABN outperformed baseline methods in terms of ID and PID. And this table shows the result for different magnetograms. Similarly, the LABM outperforms the baseline methods in terms of ID and PID. This result indicates that LABM successfully generates explanations for images with sparse important regions. Next, I will introduce qualitative results. The left column represents the input image, the center two columns and the right column represent the attention map generated by the baseline method and LABN, respectively. Right and lambda attention attending close and unrated regions. For example, right attended circumference, which included the outer part of the sun. And lambda included sunspots, but mainly attended the background. By contrast, this image shows that LABN appropriately attends the active sunspots, which are important for solar flare prediction. The conclusion is shown in this slide. Thank you for listening.